right, so this was the last example that I had given you on the last instruction about the confidence intervals. So on that example, I thought I had it queued up here. Okay, there it is. So we wanted to find an estimate for the population height of men in the U.S. So you had to find n when you knew the standard deviation was 2.5. Now that didn't come just out of the thin blue air. That I had examples using that standard deviation earlier. So 2.5 was the value we had used in the past. So that's where that came from. The E was 2 because we wanted to be within 2 inches of the true population mean. And then our confidence level was to be 90%. So that gave us an alpha value of 0.1 and an alpha over 2 of 0.05. So we did the probability here to find the z-score, the critical value that we were looking for, which is 1.645. I've highlighted the notation for coming up with that with your calculator. Then we plugged into the formula and we popped it out as being 5. Now it turns out that all heights are normally considered to be normally distributed. So as it turns out, having a sample of size 5 is not a big deal at all because we do know those height values are normally distributed. Okay, now on to our next topic. And our next topic is making estimates for the population mean when the standard deviation of the sample is actually unknown. So when the standard deviation of the population is unknown, the sampling distribution is no longer the z. So what it is something called the t-distribution, or more formally known, it's called student's t-distribution. Now, there's a lot of stories about this, but the person who came up with this distribution was a very well-known statistician, and he worked for Guinness Brewing Company. And there's a lot of reasons why he may not have published his work. Some people say that he didn't publish his work under his original name because it was forbidden. Some people think that it has to do with the fact that maybe alcohol was kind of forbidden and he was associated with some other institutions that may have been looked down on, but for whatever reason he didn't use his actual name, which was Gossett, and it became known as student's distribution or student's t-distribution. Now student's t-distribution, it approximates the sample mean still, but with a standard deviation of the sample divided by the square root of n, and it offers a much more efficient estimate when we have small sample sizes, and it's not only based upon a mean and a standard deviation, but something called degrees of freedom. And degrees of freedom is something that we'll come across in quite a few of our distributions that come later. And degrees of freedom, and your book's going to use just a DF to denote these. More advanced texts use this notation, which kind of looks like a fancy looking V. It's called a nu. And the degrees of freedom is quite easy. It's just the sample size, n minus 1. So if we had a sample of 20, so if n was equal to 20, then our degrees of freedom would be 20 minus 1. And that would be our degrees of freedom. Now most t-tables, and we've seen our t-table before, most t-tables have degrees of freedom listed up through about 30 by ones, and then, well, no, it's not 30, it's usually 20 to 25 by ones, and then they jump by fives, and then by tens, and then they start jumping more like by hundreds until they get that large degrees of freedom, which we saw earlier. Now, when the degrees of freedom are large, student's t-distribution is approximately a normal distribution. So what we say is in infinity, right, as we get bigger and bigger and bigger sample sizes as we go off to infinity, that the student's t-distribution is approximately normally distributed. And that's why we used that t-table earlier to find our inverse normal values, because it is approximately a normal distribution. So with all of that said, what does this mean for us in finding a confidence interval? Well, it really means very little except for the critical value this time. that critical value, instead of being a z alpha over 2, this thing is now going to be a t. And we're going to have some more notation. So one of the things that we need to note about it is the degrees of freedom. So this is a t with n minus 1 and then alpha over 2. And that's how we'll denote our t values, and they're critical values this time. And this is when our sigma is unknown. But other than that, the confidence interval that we're building forms exactly the same way. So our population mean is going to be between the sample mean minus a margin of error and the sample mean plus the margin of error. And the margin of error calculation, well, it only differs by one thing, the distribution, the sampling distribution, right? So my critical value is a t n minus 1 comma alpha over 2 times, not sigma, but s, and then divided by the square root of n. And that's the only differences in what we were doing before. What this means to you, however, is you have to be a little bit more cautious, because when you are dealing with the real life applications, you have to be careful. Do I have sigma known or do I not have sigma known? So if it's not, then we don't have the z distribution to fall back on. We just have to use the t distribution. So with that said, now let's go ahead and practice a little bit with just the t distribution and see how we use it. And again, in Brace's book, it's in Appendix 2, and I believe the table value hasn't changed in edition 10. I think it's still A24. So we're going to look up t values for a sample of size 23, and we want a 90% confidence level. So our 1 minus alpha is going to look like 90%, and we have an n equaling to 23. So in order to find our t of n minus 1, we've got to find that, and then we have to find our 0.1 divided by 2. So this is going to be a t with 22 degrees of freedom and 0.05. And then remember that this is one tail. Right? When you do the alpha over 2, that's what's in one tail. If we wanted what's in two tails, we just use the 0.1. So now let's go to our t table and let's look that up. So t table, and we're going to look back up here and we're going to see, okay, here's one tail, so that was 0.05, here's 0.05, and now we're going to follow this down, and we're going to follow it down until we get to 23. So our 23, let's scroll this down so you can see it. There it is, 23 right there, and that's 0.025, and this one right here is the one that we need. That's 0.05 in one tail, two tails is 0.1, right? This is alpha here, this is alpha over 2, and our value is 1.714. Now you remember that when we had the normal distribution, so if sigma was known, that our value at 90% was 1.645. So what you see here is that this value is a little bit larger, and that's because what happens with the t distribution is it is a little wider and a little flatter. So instead of having a value up here, it's a little bit further out into the tails, because these tails encompass a little bit more area because of the way the distribution is shaped. So the smaller degrees of freedom have wider, fatter tails than a normal distribution. So that's my critical value. All right, let's go do another one, and maybe you can see if you can do the values on your own this time. So what I want you to try to find is this one. For a t-table, in Appendix 2, I want you to find the critical values for a sample of size 48, for which we want an 85% confidence interval for the population mean. And you should probably pause this and do it on your own before you watch me do it, and that way you can check and see if you've got the right idea. So 1 minus alpha this time around is going to be 85%. So what we need is, for an 85%, we need alpha of 0.15, and that would mean alpha over 2 is equal to 0.075. Now this I'm not sure is going to be in our table, so we may need to use this one using our calculator. So let's see. So our n is going to be 48, so we have to do n minus 1 for our degrees of freedom, being 48 minus 1, or 47, and that's degrees of freedom. All right, so now let's go take a look at the table and see if it's going to help us or not. So we have, nope, in one tail I don't have that choice of 0.075, and this one doesn't have the area. In two tails you see either of 0.1, so this isn't going to help me at all. So there are some other choices, and one of them is using our calculator to do this. So let's go ahead and talk about our calculator. So our calculator, in the inverse, in the table we do have the inverse t. So if we do this inverse t, what it's going to need is the same thing that the z does. It's going to need that area in the tail, 0.075, that's what's in one tail, and it's going to need the degrees of freedom, which in this case would be 47. Now if you don't have a newer operating system, you may need to get a program. Now you can get programs off the internet yourself and connect your calculator to the your computer using a cable, and you can download that, or you can actually ask me for that in class, because I do have the programs and I can share them with you, and I will be doing that in class. So if you don't have it, don't panic. We can get it onto your calculator so that you can have this available to you if you don't have the newer operating system. I believe a couple of my calculators are older operating systems and don't have the inverse t. So if I plug that in and I enter it into my calculator, what I find is that my t, with 47 degrees of freedom and the alpha over 2 of 0.075, I find that value is going to give me a plus or minus 1.46, and then rounded to the nearest 10,000th place is going to be 3. And that will be my approximate value. Now remember, these critical values are plus or minus. So if when you go to your t-table, if you were using a t-table, one of the things that you would notice for this problem, is that this t-table doesn't have 47 degrees of freedom. So it jumps from 40 to 45 and then up to 50. So the convention is that we'll use the next lower degrees of freedom. So that's a note down here, and you want to make sure you know that. So you'd use lower degrees of freedom, not higher degrees of freedom, if they're not available in table. And that's what you want to make sure that you note, just in case all you have to use, or all you're told you can use, is a t-table. So lower degrees of freedom if not available. And that just compensates and makes it a much better approximation. It gives you a little leeway. It makes a little balance room in there. All right, so that's going to end this lecture, and next time we'll come back and we'll do some confidence intervals.